Once we've defined the pipeline, it's still left for us to execute it, and that requires us to invoke the .run method on the pipeline object. This in turn is going to make use of the runner that we had passed in at the start of this function. That runner could be a local runner, in which case our data flow pipeline would execute locally, or it could be the cloud data flow runner. This would cause our data flow pipeline to run on the cloud in a distributed manner, with the amount of CPU, that is compute capacity, devoted to it to be auto scaled by the Google Cloud Platform. That is exactly what this highlighted line of code does. Notice that the first argument of the preprocess method tells us how many rows we would like to sample. We've specified 50,000 rows here. As the comment there tells us, if we would like to run our pipeline on all of the data in our dataset, we've got to change that input argument to be none. That would take even longer. That would be a pretty expensive job. So we are not actually going to run that. We'll just restrict ourselves to the 50,000 lines that we want to work with. Let's go ahead and hit Shift Enter and see what happens when we try to execute our pipeline, and we find that we have an error. Let's parse that error. We see that we've had permission denied, and the message is that the Google Dataflow API has not been enabled for this particular project. The error message helpfully tells us what web page we should visit in order to enable it. So we click on that web page and we go ahead and enable the Google Dataflow API. Hopefully this is quite familiar to you if you've used the GCP or other cloud platforms. It's often required for us to enable specific APIs before we make use of them. We now go back and re-execute our pipeline, and this time it is successful. To be precise, at this point we have only submitted the Dataflow job for execution. This job can take quite a while, 5 to 6 minutes for completion. So let's go ahead and monitor the job from the web console. We switch back over to the web console in order to monitor our job. We click on Dataflow and we find there that we just have the one job going on. When we click on it, we get this nice visual representation. This visual representation tells us what we already knew, that we have two parallel pipelines going on, one for the training data and one for the validation data. Each of these pipelines is going to do exactly the same thing. That's because each of them was created inside the same for loop. Each of those pipelines is going to read from BigQuery, process each line of the results that we get from the BigQuery query, and then go ahead and write those out to CSV files in cloud storage. Of course, the output locations for the training and the validation data are different. We give this pipeline enough time to run, and then it goes ahead and turns green. The jobs have finished running. We can tell from the job summary information on the right that this particular job took 6 minutes and 5 seconds to complete. In just a little bit, we will write a more complex job which will take a lot longer. In any case, let's now turn back to our data lab, that's the Python IDE, and let's execute a few simple commands to make sure that our job did indeed deposit the files that we wanted in the locations that we had specified. Notice that in order to do so, we make use of gsutil commands. So that is executed in the bash shell. Remember, the gsutil is a Google Cloud command line utility which is going to interact with Google Cloud Storage. We first run gsutil commands in order to make sure that the files have been written out, and we can see that they have indeed been written out with names or file names in the format of a shard. That is, we have sharded files output from Dataflow. This was the result of running gsutil ls-l. Let's go ahead and actually examine some of those files and do so using gsutil cat. Notice how it's possible to use Unix commands like cat, head, and so on in conjunction with gsutil. And this gives us a peek into the contents of some of those sharded files, and indeed we see that they do contain the comma separated values that we want to input into our model. The data is ready. This is in the new format, the new representation that we wanted. We can now turn our attention back to the TensorFlow model. So let's switch back to the model.py file. We are now going to go ahead and carry out some feature engineering here. We are going to combine different columns and create a new model using another off-the-shelf estimator object called a DNN linear combined regressor. That's pretty powerful. It will have some features fed into a deep neural network, some others fed into a wide neural network, and it will nicely combine the outputs of all of those. That's coming up next.